So in this video, we're going to continue to talk about probability, but we're going to define the difference between theoretical probability and experimental probability. All right, so let's just first talk about what those two things mean. Theoretical probability, you hear the word theoretical, sorry, I spelled that, theoretical. Okay, the theoretical probability, you can hear the word theory and theoretical, and it is what should happen based on a theory, right? It's what should happen when you do a probability experiment, okay? So a probability experiment would be like tossing a coin. So it's the probability that of getting heads when you toss a coin. The probability of getting heads is 1 out of 2, or 50%, right? That's what should happen. If you toss a coin, you have a 50% a chance of getting heads. But does that always happen? No, if I toss a coin twice, I may never get heads, all right? So does that mean my probability is wrong? No, it just means that the first 2 times I tossed the coin, I didn't get heads, all right? So the theoretical probability was 50%, is not what actually happened, right? So we call what actually does happen the experimental probability. Experimental probability is what actually happens. So when you toss the coin, what happened? The theoretical probability is what should happen in a perfect world. Okay? In a perfect world, I toss a coin 2 times. 1 time I'm going to get heads, 1 time I'm going to get tails. In a experimental probability, this is what happens in the real world. I toss a coin 2 times. Maybe I get tails both times. All right? So the theoretical and experimental probability are not always the same thing. Okay? In fact, the ones you're finding today are usually not the same. Okay? They can be, but they usually aren't. However, okay, the more you toss that coin, okay, we tossed it 2 times, we got tails the first 2 times. All right? But if I continue to toss the coin, then the probability, the 50%, is more likely going to happen the more times I toss the coin. So we say that as the number of attempts in the experiment increases, the more times I toss the coin, okay, the theoretical and experimental probabilities should become closer in value. Okay, so maybe the first 2 times I never got heads. Okay, but the more I do it, the more often, let's say I do it 10 times, okay, then I'm going to get heads a few times. If I do 100 times, then I might even get it exactly 50% of the time, all right? So the more I do it, the more likely these two will be the same, okay, or at least get closer together. Theoretical, perfect world, what should happen. Experimental, real world, what actually does happen. All right, so let's see how that applies to some examples here. It says the graph shows the results of an experiment in which a number cube is rolled 50 times. All right, so number cube, remember this is my number cube. So if I just start by looking at the graph, I can see that these are the outcomes down here, 1, 2, 3, 4, 5, 6. So, and then these are how many times that number was actually rolled. Okay, so they all rolled the same amount of times. Nope. Which number was rolled the most times? Well, 2 times. So that means, is it easier to roll a 2? Well, in a perfect world, it should be the same, right, for each side. It shouldn't matter how you roll it. You should get the same, should be the same probability for any number. But when I rolled it, or when this person rolled it in their experiment, they actually had 2 more often, all right? So there's a difference there. That's what we're talking about, the difference between experimental and theoretical. All right, so we want to find the theoretical probability. Okay, when you're looking for theoretical, you're not going to look at the chart. You're not going to look at how many times they're rolled. You're just going to think about the actual die, what should happen in a perfect world. The theoretical probability of rolling a 2 is found by just figuring out how many 2s are there. 1 out of how many? 6. The probability of getting a 2 should be 1 out of 6. Should be. Okay, keyword there. Should be 1 out of 6. If I change that to a percent, if I divide 6 into 1, won't go. 6 into 10 gives once. Subtract and get 4. Bring down a 0. 6 will go into 40 6 times. Sorry, I know I'm writing over things here. 4. This is going to continue, right? So it's 16%, or since that repeats, I could round that to 17%. Okay? So in a perfect world, 17% of the time, I should get a 2. All right, experimental probability, that's what actually did happen. So now I'm going to look at my table, all right, or my chart. How many times did I actually roll the 2? I rolled it, look, 12 times. Out of how many? Well, not out of 6. How many times did they do the experiment? 50. So 12 out of 50. All right? So I can simplify that. So these are both divisible by 2. That would give me 6 out of 25. Okay? And then I can find the percent because that'll make it easier to compare. If I do 25 into 6, it won't go. It'll go into 60 though twice. 50, subtract and get 10, bring down a 0. 25 will go into 100 4 times. Okay, so as a percent, this is 24%. All right, so were the theoretical and the experimental probabilities of rolling the 2, were they the same? No. Okay, the theoretical, what should happen, is lower than what actually did happen. The 24% is what actually happened when they did the experiment. All right, if they continue, so they did it 50 times, if they did it 150 times, will these get closer together? Well, yes, they should get closer together, unless there's something wrong with your dice. Then you have a different problem, okay? But the more times you do it, the closer these should get together. All right, experimental probability can be used to make predictions about future events, okay? This is why we care about probability. It's because we can use it to predict what might happen, right? You use the probability in a, let's see, proportion to make a prediction. All right, so when you're asked to make a prediction, you're going to be using proportions. So we're going to use the graph above. How many times would you predict the cube will land on 4 if the cube is rolled 150 times? All right, so when you're predicting, you're using the experimental probability, okay, based on what has happened in the past. We want to predict what's going to happen in the future. All right, so even though we know what should happen, we're going to make our decisions based on what actually does happen, so on the experimental probability. So the probability of getting a 4, all right, was how many? It was, if I read the graph, it was 9 out of 50, all right? So that's my experimental probability. But I'm making a proportion, all right? So I'm making my boxes 9 out of 4. And I want to know how many times I'm predicting it will happen if I will get a 4 out of 150 times. Okay, so this is how many times I get the 4. This is out of the number of times I rolled it. All right, so out of here, I get the 4 9 times out of 50, and 150 times, that's going to go down here at the bottom. I want to know how many times I'm going to get the 4. Okay, that's my variable. How do you solve a proportion? By multiplying across and then dividing. All right, so if I do 9 times 150, you get 0, 45, carry your 4, 9 times 1 is 9, plus 4 is 13. All right, and then I do what? After I multiply across, I divide. Baseball, baseball bat, remember that? Okay, 50 won't go into 1 or 3, it'll go into 135 5 times. When I subtract, I get 10, bring down my 0, 50 will go into 100 2 times. Okay, so I can predict that based on my experiment, right, the number of times it'll land on a 4 is 52 times if I roll it 150 times. Okay, all right, the graph below shows the result of an experiment in which a spinner with 3 equal sections spins 60 times. What is the theoretical probability of landing on red? Okay, theoretical means I ignore everything else, okay? Theoretical is what should happen, okay? It's a spinner with 3 equal sections, all right? The probability that it'll land on red, well, there are only 3 colors, green, I know these are harder to read, green, blue, and red. Okay, so the probability of getting red should be 1 out of 3. Okay, is that what happens? Did I get these equally? Nope. It looks like you get red more often. Okay, the experimental probability of spinning red for this experiment was 24. Okay, experiment, looking at the chart now, is 24 out of how many times did they actually do the experiment? 60 times. All right, so if I go back, and if I want to compare these, it's easier to compare them as percents. I guess I can simplify this too, actually. I can divide by, what, 12? This would be 2 out of 5, 2/5. All right, so if I change these both to percents, if I divide 3 into 1, add my decimal to 0, 3 will go into 10 3 times. Okay, and then this is going to repeat, so this is going to end up being like 33%, about 33.3%. Okay, over here, if I divide 5 into 2, add my decimal and my 0, 5 will go into 20 4 times. All right, so make it a percent. This is 40%. All right, were they the same? Nope. 33%, 40%. All right, but I can use the experiment to make a prediction. All right, so predict how many times the spinner will land on red if it is spun 500 times. All right, so I have to start with what I know from the graph. When they did the experiment, red was rolled 24 times out of how many? Out of, what did it say, 60 times. Okay, I want to know how many times I'm going to get red. So what's the probability of getting red out of the times it's spun? Okay, how many times it's spun? All right, so this is what I don't know. It's my x out of 500 times. All right, then you solve it like a regular proportion by multiplying 24 times 500. Now, since we had already simplified this, if you had wanted to use the 2/5 here, you could. I'm just going to do it the hard way. Why am I doing it the hard way? All right, 0, 5 times 4 is 20. Start with a 0, 0, 0, 10. I get 12,000. I still need to divide by 60. So 60 won't go into 1, 2. It'll go into 120 twice. And then I still have these 2 zeros, so 200 times. So I would expect it to land on red 200 times if you roll it 500 times, okay? All right, if the spinner was spun 3 more times and landed on green each time, determine the experimental probability of spinning green for this experiment. All right, so now I'm ignoring the 500 times. I'm going back to my chart. All right, so originally it landed on green 21 times, okay? But if I do it 3 more times, then instead of 60 times, okay, if I do it 3 more times, now it's gone up to, I've spun it 63 times. All right, and green was 21, okay? But if I get green each time, then it's no longer 21. If I add 3 to that, I get 24 times. So the probability of spinning green, if you spin it 3 more times, okay, it would be 24 out of 63. 24 out of 63. Okay, can you simplify that? Yes, these are both divisible by 3. That would give me 8 over 21. If I want to change it to percent, oops, yeah, 21 into 8, I get 3 times, 63, 17, carry, or I'm sorry, bring down a 0. 21, I'll go into 170, 8 times 8, 68. Okay, I'm going to stop there and change it to a percent. This would be about 38%. I'm just rounding 38%. All right, so if I notice here, the total went up to 63. The green went up to 24. Okay, but did the blue or the red change? No. Okay, so 15 would still be the blue, and 24 would still be the red, okay, because they didn't change at all. So the total went up to 63. The green went up to 24 because I spun it 3 more times. It landed on green 3 more times, all right? So that raised that to 24, but it didn't change the blue or the red, all right? Let's look at the last one. A survey of Ms. Ramirez's students showed that 30 students will have pizza for lunch, 17 will have macaroni and cheese, 12 will have a hamburger, and 5 will have chicken fingers. Suppose Ms. Ramirez surveys all 1,200 students in the school. How many students can she expect to choose hamburgers for lunch? Okay, so again, this is when those predictions are handy, okay, when you're trying to make some decisions about food or cost of things, all right? It's good to know what people like, all right, so you don't buy too much of one thing. All right, so her survey showed that 30 like pizza. Well, let's just make our own little chart here. 30 like pizza, 17 like mac and cheese, 12 like hamburgers, and 5 like chicken fingers. All right, she wants to know out of 1,200, how many are going to choose hamburgers? All right, so we know that 12 in the survey chose hamburgers. All right, so this is hamburgers. Okay, out of how many? This is our total down here. right, well, to get the total, I have to add these up. I don't think it told us. So 7 plus 2 plus 5, 9 plus 5 is 14. 3 plus 1 is 4, 5, 6 out of 64. So from the survey, 64 students, 12 chose hamburgers. Okay, to make a proportion, now I'm going to do, all right, this is what I start with from my experiment. Okay, out of 1,200, where's the 1,200 going to go? Well, I want to know how many hamburgers out of 1,200, so that's the total. Right, then to solve it, I'm going to cross multiply 1,200 times 12. Start with the 2, 0, 0, 4, 2. Start with a 0, and then 2 zeros, a 2 and a 1. Add those up. Okay, and then I divide by 64. So it'll go 2 times, let's see, that's 128. That's 16, bring down a 0. Okay, 64 going into 160, let's say 2 times again. So that's 128. That's a 2, 5 minus 2 is 3, bring down that last 0. 64 will go into 320. Yep, 32. Okay, so based on the survey, right, I would expect 225 students to choose hamburgers. All right, so again, we're talking about the differences between theoretical and experimental. Theoretical, what should happen, all right, it's based on really just how many compared to the possible number, all right, that's theoretical. Experimental is what happens when you do the experiment, what actually did happen. So it's based on some type of experiment you did, a chart or some information where they told you how many times something actually occurred. Okay, we like experimental because it helps us make predictions, right? And we use proportions to make those predictions. All right, see you soon.